A bipolar junction transistor or BJT scaled current mirror circuit design is discussed in this example. It is implemented with 6 PNP BJT or bipolar junction transistors and 1 NPN. Then we have a series of 2 Zener diodes that are the core to generate the reference voltage and also help us with the temperature compensation in coordinates and in accordance with the NPN bipolar junction transistor. I'm going to talk about it. We also have one single supply in this design, in this example, Vs, that can be, for example, 15 volt, but this design can be easily a double supply design. If we desire that, then on the other side, instead of connecting to ground, we can connect to a negative supply. R1 resistor is the resistor for the bias of the Zener diodes, and also R2 resistor is the bias resistor for the reference current via this NPN transistor. The circuit mirrored the current and scale it using the combination of these PNP BJT transistors, and then at the output we have an output current I out as shown. We want to find the formula for that output current, accurate formula practically speaking, and also the output impedance R out as observed or seen from the collector of the PNP transistor that is shown here at the output of the circuit. Okay, so to quickly run the analysis, one important information also is we need to make sure that these transistors are properly matched so that we have accurate constant current coming out of the circuit with minimal temperature dependency. So it's important that if we use, for example, the packages of 7, let's say PNP, or let's say 8 PNP, or if you're using smaller packages like 4 PNP, then at least we make sure that these transistors are in the same package and these transistors are in the same package as well. So, but same type of package. For example, let's say while analog devices has its own examples and packages, Fairchild has, for instance, these options for the PNP transistors. You can have a package of matched transistors like this with 2 transistors inside the package, or even 4 transistors inside the package. So these options available from many providers and can be purchased from the likes of Mouser or DigiKey. So I just wanted to mention that. So with that in mind, we make the assumption that these, let's say, PNP transistor benefit from the same junction properties. So they have the same junction temperature and also especially the same saturation current IS, especially for these ones that are mirroring each other. So now let's go back to quick analysis of the reference voltage. Over here we have, as an example, select 3.3 volt and 6.2 volts. So if we add up together as series of Zener diodes, we have 9.5 volt as the series. So that 9.5 volt given the ground appears at the base of transistor NPN transistor here. So we have 9.5 volt here. I'm going to write it here, 9.5. Of course, this transistor is supposed to be on, and therefore we have plus minus 0.7 volt drop. So we get to 8.8 volt at the emitter of this NPN transistor. So we can select R2 to have the proper emitter current, or let's say reference current effectively. So I refer to it here, is simply given that we have ground on the other side and 8.8 on this side. So effectively across R2 we have 8.8. So that reference current is 8.8 divided by R2 on this side of the circuit. So let me just write it here, R2. Okay, so this is the value of reference current at the collector, roughly at the collector of the NPN transistor. But how can we make sure that this 9.5, which is the reference voltage coming from the series of these 2 Zener diodes, has minimal temperature dependency? Okay, as I said, let's make the assumption, for example, Vs is 15 volt. So we have good margin versus 9.5 volt. We can select, for instance, R1 to be 500 ohm as an example. So I'm going to write it here as an example. Let's say we select R1 to be 500 ohm. And with that, given the 15 to 9.5, so basically 5.5 volt drop across R1, 5.5, then we get, with the 500 ohm selected, then as a result we get about 11 milliamp current that is going as the bias current toward the Zener diodes. And if, for instance, as another example, if R2 is selected 8.8 kilo ohm, I mean, it depends on what sort of a reference current you will end up requiring from this circuit. But 8.8 kilo ohm, then we have 8.8 divided by 8.8, so we get 1 milliamp as the value for IR. What I'm trying to say is, with the 1 milliamp, assuming the beta of, or the current gain of the transistor, so I'm going to write it here, beta, which is ratio of the collector current to base current. So this is the collector current, and this is the base current, obviously, I base, and I collector, which is our reference current in this case. This is on the order of 200 easy, so for these small transistors, low current transistors. So with the 200, then 1 milliamp at the collector divided by 200 will give us the base current, which is on the order of, say, very small, 5 microamp for the base current. And the reason I mentioned that is because I am trying to remind that there is a current going this way, but that current is much, much smaller than the 11 milliamp bias current going through the effective series of R1 and Zener diodes. So we can effectively neglect the 5 microamp versus the 11 milliamp bias current. So that's why we can say effectively or practically, I'm going to write it here. So practically the R1 is in series with Zener diodes, and therefore we can just simply did exactly what I did. So the bias current IZ, let's say, so the current of Zener diodes bias is simply, as I did, Vs minus 3.3 plus 6.2 volt divided by, and then we have 500 ohm, which is 0.5 kilo ohm. So exactly as I did, we ended up with 5.5 volt divided by 0.5 kilo ohm, which gave us the 11 milliamp that we computed for the current of bias current of the Zener diodes, which is pretty good. Even if the 15 volt drops a little bit because it's not necessarily a very regulated supply voltage, then we are not worried about this guy reducing that much, and therefore these guys remain, or the Zener diodes remain, well biased. Now let's focus on what happens on this side of the circuit, the actual current meter. So I'm going to write and find out the actual formula for I out. We start from this point. We have the reference current, which is the collector current for this transistor. I'm going to name the PNP transistors like this: T1, T2, T3, and then we have, let's say, T4, T5, and finally T6 for PNP transistors. Now, I can say the reference current, the collector of the NPN transistor, I can write it this way. The reference current is equal to, there is a collector of T1, so there is this IC1, and there is also the sum of the base of transistor 1 and sum of the base of transistor number 2. So reason we are doing this is why we expect at the end of the day, at the end of the calculation, that with approximation, given that the base emitter of T3 and T4, T5, T6 are exactly equal to each other, as you can see, then we hope that, and especially given that these transistors are in the same package, so they're matched transistors, then with the same base emitter for all of them, then they should have the same copy of the collector current. So if, for example, T3 has this current, IC3, then we expect that it would be the same collector current for these guys. So that's a nature of the current meter of the matched transistors. And then approximately, we are hopeful to say that the collector current for transistor T2 at the output, basically I out, is the sum of, effectively approximately the sum of these three currents. So what I'm trying to say is, hopefully we can show that with a good approximation, I out would be 3 times I reference. That's what we are trying to get to, but since we are interested in accurate formula so that we can show also the level of accuracy, or let's say the amount of error, that's why we are chasing the actual formula. And then at the end, I'm going to quickly show how R at the output of the circuit can be computed. So let's start. IR is equal to IC1 plus IB1 plus IB2, because at KCL or Kirchhoff current law at this node, these two currents add up together and end up entering here, and then we'll add up with IC1 to get to form the IC at the for the collector of NPN transistors. So I can say IR is equal to IC1 for this transistor plus IB1 for that transistor as well, plus IB2. Okay, so I used KCL here, but we know that IC1 plus IB1 is basically IE1, the emitter for, so the current of the emitter for transistor 1. I'm going to write it here. So IE1 plus IB2. But the nice thing is IE1 for transistor T1, I'm going to use a different color so that it's observable. IE1 for transistor T1 is equal to IC3 for transistor T3 just because of the way connection is there. So I can write as a result, instead of IE1, I can say it's equal to IC3. Also, keep in mind that the IB2 for transistor 2 is simply I out, which is the collector current of transistor T2 divided by beta. As I said, we make the assumption that beta for all transistors is the same, which is the gain of the current gain of single transistors. So I out obviously is just beta times IB2. So therefore, I can also say IB2 is I out divided by beta. So let me then rewrite the formula. So IR, reference current, is equal to IC3 plus I out divided by beta. So what next? Well, IC3, as I said, these 4 transistors at least, T3, T4, T5, T6, these PNP bipolar junction transistors are in the same package. They are matched transistors. So if they have the same base emitter base voltages, as they do here, then because of the Shockley PN junction equation, which says voltage of base emitter, or basically, let me write it this way, the collector current of a PN junction of a bipolar transistor is equal to saturation current times e to the power the voltage of base emitter or emitter base divided by the thermal voltage VT, which at room junction at the room temperature is roughly 25 millivolt. Okay, so with that said, this is referred to as Shockley PN junction equation. So Shockley PN junction equation. And because of that, since we have the same emitter base or base emitter voltage for these 4 transistors, and since they are on the same package, so they benefit from the same junction property, they have roughly the same IS, which is very temperature dependent. So collector current is equal for these transistors. I'm going to write it here. So let me put it this way. We know IC3 equal to IC4 equal to IC5 equal to IC6 because these 4 transistors are matched transistor in the same package. Matched PNP in the same package. Integrated circuit, basically. Okay, so with that in mind, I can then substitute IC3 with IC6, this guy, for the collector current of this guy, so IC6. That's fine, let's do that. So I'm going to get then IR, or the reference current, equal to IC6 plus I out divided by beta. Well, what is now relationship between the emitter of transistor T2 versus as a function of IC6? okay, take a look at what's happening. We have 3 copies of IC6 as we talked about because of, as I said, the Shockley-P junction equation and the fact that these transistors are mirror of the reference T3 transistor. Then we have 3 copies plus we have 4 base current. So we have I base 3 and we have 3 copies of I base 6. But then I base 3 is also a copy of I base 6. So basically here we have 4 copies. I'm going to write it probably here is the best place. So 4 I base 6. Okay, nice. So at this node, the emitter current of, let me move the I out a little bit down. Okay, now better. I have some space. So what I can say is this current here, the I emitter of transistor T2 is equal to, so maybe I write it here. I know the using KCL at this node at the emitter of transistor T2, so Kirchhoff current law or KCL law of preservation of current at emitter of PNP transistor T2 give us the emitter transistor of T2 equal to, is equal to, of course, let's say beta plus 1 over beta, the collector current of transistor T2. That's just basically saying, if that is not clear, let's put it this way, is I collector of T2 plus I base of T2. That's obvious. That's by definition of transistor PNP. And then we have IE2 KCL at this node equal to 3I collector 6, because as I said, there are 3 copies. And then we have 4I base. So we have 4I base transistor 6. Basically, as I said, I'm writing KCL here. This is one node in the circuit. Okay, so we know that, as we talked about it, we know that I base 2, as I mentioned here, is I out over beta. And IC2 is simply I out. That we know. So what I can then do, if I shift this up a little bit so that I have in space. Okay, so now I'm going to substitute. I'm going to get, as a result, I get I emitter 2 is equal to 1 plus 1 over beta I out, and then equal to, I just cleaned this up basically, and then let's keep this, but then use the same idea. I'm going to just substitute from what we found. So basically IB6 is IC6 divided by just beta. So it's going to be 3 plus 4 over beta. So IB6 is obviously IC6 divided by beta. Okay, so in summary, I managed to prove that IC6 is equal, just reshuffling things around, move these to the other side to find IC6 as a function of I out. So, and then just 3 beta, just make sure I'm not missing something. Okay, so IC6 is equal to beta plus 1 divided by 3 times beta plus 4 times I out. This is what I needed. So let's refer to this. So we had equation 1. Let's refer to this as equation 2 and substitute for IC6 using equation 2 and in equation 1 applied. So I'm going to use equation 1. Let me change the color back to black. So in equation 1, I'm going to substitute the information from equation 2. I get reference current equal to beta plus 1 divided by 3 beta plus 4, and then we have times I out, and remaining component or term is I out over beta. So let's clean up, and becomes I reference equal to, finally, we have beta squared plus beta divided by 3 beta. Let's just make sure I'm not missing something. Okay, so beta squared plus beta plus 1. And then we get 3 beta squared plus 4 beta and times I out. And the last step is just representing I out as a function of I reference, which is obviously 3 times beta squared plus 4 beta divide by beta squared plus beta plus 1 and times IR. So there you go. We found the accurate formula, practically accurate formula for the definition of the output current I out, source current, as a function of the reference current, which then we can use the substitution from, say, equation 0 here. So it's 8.8 divided by R2. So I'm gonna just, let's say in this reference equation here, I am going to use it instead of IR. So it will be, let me just substitute for IR. IR is 8.8 volt divided by R2. There you go. So this is what we were looking for. In practice, we can have many options. If this is a discrete design, then maybe we can have a digital potentiometer, or if you want analog potentiometer, but something accurate in place of R2 so that we can have some programmability into the design of this circuit if we want. If this is an integrated circuit, then we have different options in terms of integrated circuit design for R2. If it is discrete, again, either this is a digital potentiometer or it can be just a thin film, let's say, resistor that has a very good accuracy. Those resistors can provide 0.01% as low as that precision for the value of the resistor R2. So they are referred to as thin film resistors or precision resistors. So that's an option to have if accuracy of this R2 matter to us. If that is desired. So basically we have a good control on the value of R2. If temperature sensitivity of this matters, then we can also consider that in the calculation. Let me go back to the temperature adjustment to make sure that why this 9.5 volt is very stable, so that we make the assumption that 8.8 or whatever it is going to be relatively temperature independent. Well, let me show you the Zener diode. So the choices are 3.3 and 6.2. If I go back to the bottom, I have reference Zener diodes, say, from Vishay. Again, there are many providers. This is not the only one, but this is an example because I can quickly show the temperature coefficients. So one Zener diode is 3.3, the other one is 6.2. There you go. If you go with 3.3, you're selecting this Zener diode. And you can see that this Zener diode of 3.3, the part number 1N5226 from Vishay, has a temperature coefficient of negative 0.07%. So that means we have, let's say, 3.3, and then we have, let's say, 1 minus, where is this one? Let's say 1 point, as an example, 1 minus 0.07 divided by 100. That's how the actual voltage of, nominal voltage of this Zener diode is changing, because it has a negative temperature coefficient. The other Zener diode has 6.2 volt. So if you go back to the list of table for this specific provider, you can see that it's talking about the 6.2 volt Zener diode here with the temperature coefficient of positive 0.045. So in this case, it's nominal 6.2 volt. And times 1 plus 0.045 divided by 100. That's how the Zener diode voltage is changing. So see, we have a negative and positive. So we can adjust them. I'm not saying this is the best choice. I'm just trying to showcase that we can adjust them in such a way that the result outcome, let's add them together because they are in series. So it would become, let's say, 3.3 plus 6.2, that is our 9.5, and then nominal, plus the temperature adjustment section, which is 6.2 times this guy, so times 0.045 minus 3.3 times let's say 0.07, so 3.3, so 3.3 times 0.07 and then divide by 100. So this is the sort of nominal independent of temperature, and this is the part that is depending on temperature. We don't want this to be zero in this circuit. In some circuit we want it to be zero. In this circuit we don't want this to be zero. So we want it to be as close as possible to say what we believe is the base emitter of this transistor temperature variation with respect to temperature. For example, we know that the base emitter of NPN transistor is dropping by about 2 to 2.5 millivolt, depending on the type of transistor, about 2 to 2.5 millivolt per degree Kelvin or C. So we have, let me put it here. So basically we have an effective Zener diode, which is nominal 9.5 volt. And then we have a NPN transistor. So for this nominal Zener diode, we have this temperature overall variation. For the, and then resistor here. For the, let's say the junction of this transistor, we have the base emitter VBE that is actually dropping with roughly on the order of -2 to -2.5 millivolt per degree C or degree Kelvin of junction temperature. So what we want is this overall Zener diode, we want to have a effective temperature coefficient that is matching this result. So what is the meaning of that? I mean, that 9.5 times 1 plus 1 minus, because it has to be a negative temperature coefficient effective overall, 1 minus some temperature coefficient divided by 100 should be equal to one of these numbers, I mean a number in this range. So with that in mind, we can select the specific Zener diode values from the table so that we get the corresponding positive and negative temperature coefficients, so that the result of this becomes equal to what we like to see here that matches overall this sort of a variation. So that's what we try to achieve in this example. If adjustment needed, you can change the value of these guys using, for example, the table we have here or any other table you have from other Zener diode providers, that then you can make the adjustment. Okay, so I talked about the current then, and also how we do the temperature adjustment as I mentioned. Then the next step here is a little bit more accuracy. So, I mean, a little bit more practical estimation, sorry. So if we, for example, let go of this little 1 compared to beta and beta squared, because beta is 200 or 100 for these transistors at least. So therefore beta squared is 10,000, beta is 100, 1 is negligible. So if we do that, it is with a very good reasonable approximation, you get to basically you get to basically 3 plus 1 over beta plus 1 times the I reference, which is 8.8 volt, divided by R2. So this is basically our I reference. You can see that that 3 showed up. So effectively the output current of the circuit is practically, this output current of the circuit is practically equal to 3 times reference current, which is 8.8 divided by R2, and then there is an error term, roughly the approximate error term 1 over beta plus 1, which is pretty small. You're talking about, even if you assume beta 100, which is lowest, I would say minimal of beta in these designs for these small transistors would be 200-ish. So with this, you're talking about 0.01 versus 3. So definitely a good practical approximation. Easily would get rid of this guy saying, okay, this is negligible, so we get 3 times I reference. Okay, so the last thing to do quickly, I don't want to do a detailed, let's say, theoretical calculation, but let's say we just want to get a grasp quickly of what is the output impedance or resistor of the circuit as seen from the collector of transistor T2. Okay, so what happens is when we have this sort of a connection, as you can see, at the emitter of this transistor, and we are seeing the bunch of collectors and then wired to the base, then what happens is proportional to the base of the base resistor or the equivalent resistor of these transistors will show up at the collector of them and at the emitter of this transistor. So all I'm trying to say is effectively from perspective of T2, it's as if you're talking about T2 like this, and then there is an equivalent resistor and then AC ground. Because when we are talking about R out, we are doing an AC analysis. So we have sort of a resistor at the emitter of this transistor connected to ground with a value that is proportional to the base resistor. So it's going to be equal to, and the base resistor is known to be, let's say, V threshold, or basically the junction thermal voltage divided by the base DC current. So that is the value of this resistor. Alpha is just a ratio, is just a coefficient, meaning that it's proportional to this value. We know that when we have this sort of a connection, of course, there is feedback involved in this circuit because via this route, there is a feedback. But as I said, I don't want to deal with the theoretical complication. I just wanted to get a ballpark estimate for R out quickly. So we know that T2 has an effective resistor between emitter and collector, which usually is referred to as R out. This is not between ground. I'm connecting it between the emitter and between the collector of the same transistor. So this R out is coming from the fact that we are saying the current of collector versus the voltage of, let's say, emitter collector of the PNP transistor looks like this. So in the range that we are utilizing in the IV curve, there is a slope. Is not a zero slope. It's a non-zero slope for practical transistor, and the value of this is basically R out. If it is perfectly horizontal, it means R out is infinite. So R out is a finite value indicating that there is actually some slope here. That R out is from early effect, which is early voltage divided by the bias current, DC bias current of that transistor. So this is the DC bias, this height. Okay, so this VA, I'm going to write it here. This VA is equal to early voltage divided by IC divided by IC, or the collector current of T2. So what? Well, the last thing I need to mention is this R out practically is equal to, so I am going to write it here. Let me remove this guy because I just explained it. So R out is approximately equal to or proportional to this resistor that I just showed you at the emitter of the corresponding PNP transistor or by BJT transistor. So it's going to be alpha times VT divided by I base, that resistor, times approximately GM of transistor times RO. So let's substitute. Alpha VT IB. GM of transistor is for T2 is again AC parameter. It's just the conductance of the transconductance of the transistor is going to be just simply IC over thermal voltage of the PN junction. R out, as we talked about, is just early voltage divided by IC. So it's VA over IC. See what's happening? IC cancel out with IC, VT cancel out with VT, and effectively we get that R out is equal to alpha times V early voltage divided by I base. Now, the beauty of this is usually the early voltage of, let me just remove this or move this actually to say a better place so that I have some more space for this last conversation. This is enough for me. Okay, so I'm gonna move this also as well here. Perfect. So what's happening is this early voltage is usually on the order of 200 to 250 volt for nominal BJT transistors. So we are dealing with alpha 250 or 200 volt, let's say, divided by the base current. Well, we just designed the reference current to, we just designed the whole thing to have a 1 milliamp reference current, and we just learned that it's the output current, which is the collector current for T, which is the, which is the collector current for, so the output current, which is the collector current for T2, because it is here, I out. The output current is equal to 3 times the reference current. So if reference current is, let's say 1 milliamp, the output current is 3 milliamp. So, and the reason I say that is because then the base current is the output current 3 milliamp divided by 200, that's the beta. So I'm going to write it here, I out divided by beta. So if we substitute, we end up with alpha times 250 divided by 3 milliamp divided by 200. And if you compute this, you would end up with, so remember, this tree is 3 milliamp. So this is 0.003, and then we have divided by 200 the beta. So as a result, what we get is on the order of, that's a very sizable value. So you're talking about 200 going on top, and then we get 50,000, and then 50,000 times 3 give us 150,000, and then that, So what we get is on the order of, just to make sure I'm not missing something. So we get 500, 5,000, 50,000, and then 50,000 divided by 3 will give us, let's say, 17,000, and then 17,000 times 1,000 will give us 17 meg. So that's what I wanted to find. Alpha times 17 mega ohm. Alpha is just, again, a coefficient of proportionality. Like it can be 1, 2, it can be it can be 1/2, 1/3, depending on the design. So, but what I'm trying to say is the output impedance is on the order of tens of mega ohm, which is sizable. So the amount of resistance observed from the collector of transistor T2 is on the order of tens of mega ohm. Okay, I hope that this example, that is detailed analysis of the BJT scaled current meter, in this case the current meter with gain, in this case gain of 3 for the output current as a function of the internal reference current of this device, is helpful. Thanks for watching.